So yeah, thank you for the introduction. I'm going to talk about exponential quantum space advantage for maximum directed cut in the streaming setting. We changed the title a bit. And yeah, as you said, this is joint work with John Kelleher and Audrey Sparek. So let's start with introducing the model. In the streaming setting, we are designing algorithms for very large data sets where input is given one piece at a time. And by very large data sets here, we mean that they are too large to fit into the memory and then get analyzed. And by one piece at a time, we mean that the input is given as a sequence of updates. Think, for example, about an internet router that has a very, very small memory and needs to analyze the internet traffic going through. Or we have a huge social network and just a bit of resources to analyze it while getting the updates of the form like Alice is friends with Bob, Bob is friends with Charlie, and so on. So, in this model, in general, we are focusing on the space complexity, not the time complexity. And our goal is to design an algorithm that uses sublinear space in terms of the length of the input, and preferably it is Paul logarithmic. Streaming algorithms have been studied in the classical computation a lot, but one can argue that for the quantum computation, space complexity is even more important, which leads us to quantum streaming setting, where we assume that our algorithm can store a quantum state. In this talk, we will still assume that the input and the output of the algorithm are still classical. And our goal, again, is to minimize the space usage. Why do we think this model is important to study? So the first thing, as I said, we probably want to be able to optimize the usage of qubits because qubits are pretty expensive. We don't have too many of them. And the second one is, in this model, we can get a provable quantum advantage. So we are not only able to design efficient quantum algorithms, but we also can prove that the classical computation unconditionally is not able to do something. So, as usual, with quantum advantage, we would like to get an exponential quantum advantage, and we would like to get a quantum advantage for a natural problem, so a problem that people are interested in. So what's the state of the art with this? There are a couple of works that showed exponential quantum advantage, but all of these works showed this specifically for problems that were designed specifically to show the separation. And on the other hand, there are some works where the problems were natural, but the advantage was just polynomial. In our work, we show that for a very natural problem of approximating the value of maximum directed cut, one can get exponential quantum space advantage. So, what is this problem? In the maximum directed cut problem, we get a directed graph on n vertices, and our goal is to divide the vertices into two sets, one blue and one orange on the slide, in a way that maximizes the number of edges that go from the blue to orange vertices. And in this talk, we are going to assume that the output, the thing that we need to compute, is only the value, the number of edges that we cut. This problem isn't p-hard, and because of this, we are going to consider the approximation of this problem, where our goal is to output something that is at least alpha fraction of the optimal solution. In the RAM model, under the unique games conjecture, there exists some alpha such that approximation up to alpha is possible in polynomial time, but any approximation better than alpha is NP-hard. And the best known algorithm for this that we have is giving us 0.874 approximation. But we want to look at this problem in the streaming setting. And there are a couple of restrictions that the streaming setting is giving us. The first one is that we are not able to access the whole input at once. So we are getting the input as a sequence of edges in arbitrary order. The second part is that we don't want to be able to store the whole graph. We want to get an approximation in sublinear space or in even polylogarithmic in terms of the number of vertices. So the approximation factors that we are able to achieve are going to be a bit more modest. First, note that 1/4 approximation is trivial because if we take just a random partition of the vertices, it's going to cut 1/4 of edges. It was shown that up to 4/9 approximation is achievable in polylogarithmic number of classical bits, and that anything better than 1/2 requires linear space even in the quantum streaming setting. Anything better than 4/9 requires square root of n classical bits, and this is tied to up to 0.484 approximation in the classical setting. But notice that this lower bound does not generalize to the quantum setting. And this is basically the gap where the quantum advantage is possible. In this work, we show that the same approximation factor as the upper bound for the square root of n is achievable in just polylogarithmic number of qubits. And with the lower bound, it gives us the exponential quantum advantage. Notice that we have the same approximation factor as the upper bound in the classical setting. And that's the reason for this is that we are approximating the same set of statistics about the graph. This set of statistics we're going to call a snapshot of a graph. On a very, very high level, we are going to divide the vertices of the graph into constant number of classes. And then we're going to need the succinct representation of this graph with respect to this partition into classes. So we are interested in how many edges are going from the vertices from one class to another class. This partition is going to depend on the bias of the vertex. So the bias of the vertex is the difference between its out degree and its in degree normalized by its total degree. And this value is always somewhere between -1 and 1. Let's say that someone has given us a way to partition this interval into constant number of buckets or bias classes. Then we can divide the vertices of the graph into constant number of classes. And then the snapshot with respect to the partition to the bias classes is going to be a histogram of the number of edges that go from one bias class to another. Note that this is basically the same succinct representation that I was talking about before. It was shown that there is a way to divide this interval from -1 and 1 into constant number of bias classes in the way that gives us that the snapshot with respect to this partition gives us a 0.484 approximation of maximum directed cut. And in the classical square root of n upper bound, the authors showed how to compute an approximation of this snapshot in low space in a way that makes the previous results still work. We are going to also approximate the same snapshot, but just in just a bit of a different way. And that's basically is going to be our goal. To start with, let's look at how the snapshot evolves during the stream. So in the beginning, we have no edges. We have no edges in the snapshot either. We are getting one new edge, and this edge is going to increase the number of edges recorded in the snapshot. But also, every edge may change the bias classes of the endpoints, which is not going to only affect the snapshot cell that this edge is going to be added to, but also may affect other snapshot cells. So for example, the blue edge is going to jump to a different cell with the new edge. So if we want to be able to approximate the snapshot in the stream, we need to take care of both the values in the snapshot and the changes in the biases at the same time. And with a bias snapshot, we have a lot of jumping around. Let's look at a bit of a simpler problem that still captures these two properties that we need to take care of two properties simultaneously. We are going to estimate the number of edges that have the degrees above some fixed degree thresholds. Okay. So the way that we are going to do this is the following. Let's take one vertex and let's copy a state that corresponds to this vertex, the number of time equal to its degree. And we're going to have a stack corresponding to this vertex. Actually, we're going to have two. One for treating this vertex as a head of an edge and one as a tail. Why would we want to have this kind of thing? So let's say that we are getting an edge UV, and we have a state that is a sum of two stacks. One is a U and head, and another is V and tail. Then if we measure it with basically an Adam's measurement, then we would be able to construct a random variable that has a bias that is proportional to the indicator of UV having the right degrees, having the degrees above the thresholds. But we cannot really have this kind of state with just like sum of two stacks for all possible edges, because we don't know in advance what edges we are going to get. Instead, we're going to have a bigger state in terms of the number of stacks in it summed up for all of the edges. This is only going to take logarithmic number of qubits. Now, why are we actually doing these stacks? Why we are not just remembering basically the top of the stack and that's it? That's because this is much easier to maintain in the stream. So when UV arrives, we need to update 4 stacks. To do that, we are just going to push the whole stack for all of the 4 stacks one step up. And then we're going to add one more state to the bottom of the stack. All of this can be done by unitary transformation. And then if we go back a bit to the measurement, we have this one big state that has the sum of all of the vertices. We're going to measure it basically with the same Adam's measurement. And there could be 2 options. The first one, we're going to get one of those 2 vectors. This will destroy the state. It will destroy all of the information about all of the other vertices. But this will give us a sample of an edge with the properties that we wanted that we can use later for the classical post-processing. Or we maybe get a complementary projector. In this case, it will modify the state and will erase the top element in the state, in the stacks. But this will allow us to continue with using the same state for the later edges. So this will give us an option to count the number of edges with degrees above the thresholds. If we just do this basically 4 times, we would be able to count the number of edges within some kind of ranges. But we don't want to count the number of edges with just the degrees in some ranges. We want to count the number of edges within specific bias classes. So we want to add something else into the tracking, and that's going to be the out degrees. So, unfortunately, we cannot process the out degrees the same way that we do the degrees at the same time in the polylogarithmic space. Instead, we're going to store the out degrees in the higher order bits of the stack height. And let me show you what do I mean by that. So let's say that we are fixing ourselves to a degree range from D to D prime. Then when an edge UV arrives, first, we're going to update the degree, so just increase the stack by 1. And then with probability 1 over D, we're going to update the out degree by adding D prime to the stack. Then if we do this consistently for all of the vertices and edges, we basically with this same type of atomized measurement, we would be able to get the estimate of the number of edges with the specific degrees and out degrees. So we got a bit higher. And if we repeat this polylogarithmic number of times for different degree ranges and degree and out degree ranges, we would be able to estimate the bias snapshot. And then using the reduction that we saw in the beginning, or like the statement in the beginning, we will be able to approximate the value of maximum directed cut. So to summarize, we designed a quantum streaming algorithm that 0.484 approximates the value of maximum directed cut in polylogarithmic quantum space. This, with the classical lower bound, gives us an exponential quantum space advantage. And a couple of questions to conclude. The first one is to decide the streaming complexity of maximum directed cut. Our approximation, our algorithm gives a 0.484 approximation, but we know that anything better than 1/2 is not possible without the linear space. What's going on in between, we have no idea. And the second is to characterize which CSPs allow quantum advantage. So for maximum directed cut, we were able to get exponential quantum advantage. For an undirected version of this problem, maximum cut, no quantum advantage, even polynomial advantage, is possible. So what are the properties that allow at least some kind of quantum advantage to happen, and preferably exponential quantum advantage to happen? And that's it. Thank you for your time.
Thank you for this very nice talk. We now have some time for questions.
Thanks for the talk. Quick question. So estimating the bias for each vertex, like in general, is noisy in the streaming setting, right? So is it possible that the error can just build up, right? So how would you address that?
By noisy, you mean the fact that we can maybe sometimes basically be somewhere near the bucket, near the end of the bucket, and maybe do not jump to the right bucket because we are just nearby. So we actually are adding a bit of a noise to all of the estimates that we have, a random noise that is independent from the graph itself. And we show that this is enough on average to give us the right estimation.
So it does not blow up, like if because you're especially in the streaming setting, right? So if you're doing like taking these snapshots, it's possible that over the number of
we also repeat this a bunch of times. We repeated polylogarithmic number of times to decrease the variance, but we don't need to repeat it more than polylogarithmic number of times.
Thank you.
Thank you very much for your presentations. I just want to get the general ideas. So first of all, I just want to have an ideas why the polylock is not available in the classical setting, and why is it possible to do that in quantums?
So the reason why, basically the reason why the lower bound in the classical setting does not generalize is because the lower bound is based on the Boolean hidden matching problem, which was designed specifically to show the separation, exponential separation between the one-way communication complexity in quantum setting and classical setting. So basically in the quantum setting, we can there is a protocol like Paul logarithmic protocol. In the classical setting, nothing better than square root of n can be done. And this fact, that basically the fact that we, the authors of the lower bound, use this thing as a their source of the hardness, allows us to get some exponential advantage.
Thank you very much.
Hello, thank you. I have a question about the time complexity as well. So if you compare, for example, the space-time complexity of the classical and the quantum algorithms, is there still like a total advantage when you multiply them, or is this just about the space?
That's a good question. So I'm not quite sure, but the good thing is that, so while we are processing the stream, all of the stuff that we are doing is not taking too much time. Like we're basically doing like one unitary transformation and one measurement, and that's it. And like even in the classical post-processing, we're also doing like very, very simple things. And only after we're done and have the actual snapshot that actually can be stored pretty succinctly, we are doing the maybe more time consuming part. But unfortunately, I don't remember what's the time complexity of that step.
Do you have any intuition of how much compression you can get in the region above a half?
Above a half?
Yes, if you can do, you said you cannot do better than a half without being linear, but can you say something about like if you need an exponential number of qubits, if you can get a polynomial compression, exponential compression, maybe in that region, or?
I think there is basically I could be wrong, but I believe that the lower bounds for the classical and quantum are basically the same. But maybe my co-authors who authored the paper for the lower bound know better. Log factors, okay.
Okay, thank you.
I also have one question. I was wondering if you could give us a little intuition about this discrepancy between max cut versus max directed cut.
So I guess the only piece of intuition that we have is that, so basically for the max cut, the best that we can do without the linear space is the trivial solution. In the maximum directed cut, there is a gap between the trivial solution and the linear space. And that's it. At least I don't have a better intuition why we are able to get the advantage in the maximum directed cut and we are not able to get an advantage in maximum cut.
I see. Thank you. Any other questions? If not, let's thank the speaker again.